Imagine you are a paratrooper, dropped into a jagged, treacherous mountain range in the dead of night. You have no map, no GPS, and a thick fog restricts your vision to just a few inches in front of your boots. Your mission is desperate but simple. You must find the absolute lowest point in the entire valley, the point of zero loss. Here is the paradox. From our vantage point, as the architects, we act like gods. We can see the ridges, the cliffs, and the solution. But the model is blind. It doesn't see the shape of the terrain. It only knows where it stands right now. A list of coordinates frozen in the dark. One wrong step isn't just a detour. It's a catastrophe. A random guess could send the error exploding upward. So the question is, how do we find the way down when we cannot see the path? To solve this three-dimensional nightmare, we need to simplify. Let's freeze the world and slice the mountain right where we stand. By ignoring all other directions and looking only along this cross-section, the terrifying mountain collapses into a single, harmless line. Now we are in 2D. Here is our hero, still blind. It cannot see the valley floor. It only knows the single number describing its position. Imagine walking in pitch darkness. You don't know if the valley is to the left or right. A random step could send you climbing up the wrong wall. But we have a tool. Calculus gives us a virtual cane. We can tap the ground right here to feel the tilt. This angle is the derivative. It tells us exactly how steep the ground is at this specific point. If the cane points up to the right, we have a positive slope. Going plus means going up, but we want to go down. So we reverse the sign. Positive slope, we step negative. The hero slides to the left, closer to the bottom. Now imagine we start on the other side. The cane points down, a negative slope. Going plus actually takes us down. This is the algorithm. If the slope is negative, go positive. We always subtract the gradient. In one dimension, the gradient isn't a vector yet. It is just a sign. A binary compass telling us, not that way, this way. But the real world is not a flat line. It is a surface. Let's unfreeze the rest of the mountain and return to the reality of our problem. We are no longer dealing with just one input. We have two, x and y. Or in machine learning terms, weight 1 and weight 2. Standing here, we can't just move. We need a system. Imagine a control panel. We can't move diagonally yet. We only have two specific knobs. Let's grab the first one, the x variable, and give it a nudge. Notice what happens. We are strictly moving east. The ground here is steep. We can measure this specific slope. It tells us the sensitivity of the error to the x variable. Now, reset. Let's touch the second knob, the y variable. We move north. The terrain here is completely different. It might be flatter or even sloping down. This is the essence of partial derivatives. We don't try to understand the entire mountain at once. We slice it. We ask, does the error go up if I tweak x, and does it go up if I tweak y? Okay, we have our two separate slopes, the steep slope east and the gentle slope north. But on the mountain, we are not restricted to grid lines. Let's flatten the world to see the map. We take that steep east slope and turn it into a long x vector. We take the gentle north slope and make it a short y vector. Now we simply combine them, tip to tail. The result is this new diagonal arrow. This is the gradient. It is the synthesis of our separate controls. But what makes this specific diagonal direction special? Why this angle? It turns out this arrow points directly up the steepest face of the cliff. Let's prove it. We will spin a ghost arrow 360 degrees around our hero, measuring the slope of the terrain at every single angle. Watch the slope. Shallow, getting steeper, peak, right there. When we align with the gradient, the climb is maximized. This is the direction of steepest ascent. The gradient acts as a local compass. It takes our separate observations and fuses them into a single truth. The top is that way. So we have our compass, the gradient, a combined vector that points directly up the steepest cliff. But remember, we are not hikers trying to reach the summit. We are paratroopers trying to find the valley floor. Going up increases our error. We need to decrease it. So we do the simplest mathematical trick in the book. We reverse the arrow, we flip the sign. Positive becomes negative, negative becomes positive. Now, we take a step. Not a giant leap, just a cautious nudge in this new downhill direction. We arrive at a new coordinate. The terrain here is different. The old compass reading is now garbage. So we recalculate, we feel the slope again. We find the new steepest ascent and immediately reverse it. Step, calculate, flip, move. We repeat this loop over and over, tracing a path that zigzags through the darkness, sliding inevitably towards the bottom of the valley. This is the algorithm. New position equals old position minus the gradient. But here's the catch. In deep learning, we don't just have two weights like x and y. We have millions. We can't draw a million-dimensional mountain. Our primate brains stop working after dimension 3. The map collapses. The blind hiker is no longer just a metaphor. It is our literal reality. We are floating in a void of a billion parameters. But the math doesn't panic. That massive list of partial derivatives, it still condenses into a single object. A single arrow. It doesn't matter if the space is infinite. The gradient cuts through the chaos and points exactly up. So we simply flip it. We take a step downhill, and then another, sliding through the dark, guided by this mathematical compass. Until finally, the gradient fades to zero. We stop. We have reached the bottom of a valley we never saw, but successfully conquered.